And tell me, what did they find? What was a good fit for the star mass? What number did you move that blue bar to? Or this blue bar. 84, 84, 98, 86. Cool. So there's some flexibility here. Let's go maybe 88 kind of in the middle. How about the dark matter mass? What should I set that to? 13, 11, 13. So maybe split the difference, go for 12. Yeah, so that's a pretty good fit. I haven't played around with the point mass in the center. That would be if this galaxy has a central supermassive black hole, which it probably does because every galaxy seems to have a central supermassive black hole. But with this data, we can't really measure whether or not it's there very well. We just don't have good enough resolution of the center. But what we can see is that without dark matter, you cannot fit this kind of long tail. So then for your ratio, the idea is we take 12 times 10 to the 11th. So 12 times 10 to the 11th divided by 88 times 10 to the 9th. So just this Wolfram alpha, 12 times 10 to the 11 divided by 89 times 10 to the 9th would give us a ratio of around 13, 13.5. So there's 13.5 times more dark matter in this galaxy than there is star mass. So that is kind of the point of this, is that to fit this curve, you need dark matter, and you need quite a bit more dark matter than stars in order to make things work. Any other questions about any of that? And that's kind of exactly what Dr. Vera Rubin did. She measured those rotation curves and then saw that that long tail told her that there must be something besides stars in these galaxies. Okay, so that was our first method for detecting dark matter, was measuring rotation curves. Our second method is going to be using gravitational lensing. So rotation curves, the thing with those is they only work for spiral galaxies that have nice organized rotation. Gravitational lensing will also work for elliptical galaxies. So this is going to be how we measure the mass of elliptical galaxies. And what gravitational lensing is that, so according to general relativity, we exist in a space-time fabric. And what gravity is it's curves in that space-time fabric. So when you take something with mass and you put it in the space-time fabric, it bends the space-time fabric. And the more massive your object is, the more space-time bends around it. So this is kind of like if you have a trampoline and you put a bowling ball in the center of it, you get kind of a dip around your bowling ball in your trampoline. And if you then rolled a bunch of ping pong balls around it, you would see them kind of curve around that bowling ball. It's kind of hard to picture because we need this three-dimensional fabric that exists everywhere, and when we put heavy things in it, they all fall towards it, and that's what gravity is. But the important thing is that light will curve around these. The important thing, mass curves space-time. The more massive you are, the more you curve space-time, and light will travel around those curves. So if you have something really heavy, if you have something really heavy, it bends space-time like a galaxy or a galaxy cluster. And if we can measure the light from an object behind that and see how much it is curved, we can tell how massive the thing in the center must be. So to show that another way, here we have a galaxy cluster, a big galaxy, and it's bending space-time. So it's kind of acting like a lens. And like if you had a magnifying glass, it pulls light down to a point. These lenses kind of work the same way. Light curves around massive objects through space-time. And so we can use the amount that light is curved to measure the size, the mass of the thing curving the light. And just a few examples of this. So these are images of different gravitational lenses where we have a massive thing bending light from objects behind it. And the next one's my favorite. It'll show up really quick. So the smiley face, Hubble smiley face, where you have two massive galaxies bending the light from the objects behind it. So we can measure the amount that this galaxy light is curved to show how massive the center object is. So this is just another way where we're comparing the mass we measure using this time gravitational lensing instead of rotation curves to the amount of light we see, and we find a big mismatch. So when we use gravitational lensing to measure the mass of elliptical galaxies or galaxy clusters, we see there's a difference in the amount of, we see too much mass. They are bending space-time too much for the amount of light we see. So these mass to light ratios, again, are just too high. The same kind of thing like you just did, except now with a different method for measuring mass. And that must mean that there is some missing mass, some dark mass, or some dark matter. So that's our second method. This one's a little funky to think about, but the big point is that we can use curves in space-time to measure mass, compare that mass to the amount of light we see, and find this difference that tells us dark matter, again, must exist. Any questions about that? And I'll just put a little plug for, I think, the only lab I haven't talked about yet. In the black holes and curved space-time lab, I walk you through how to make your own little model of curved space-time. It's a little tricky. Usually I do this with a big sheet of stretchy fabric that I cannot send in an envelope because it is multiple feet across. But there are some things that you probably have in your home that can also work as a model for curved space-time. So if you want to try to play with that, that is another option to get some lab points. So our next method for observing dark matter is by looking at colliding galaxy clusters. So we've done spiral rotation curves to see that there's too much mass for the amount of light. We've done gravitational lensing to again see that there's too much mass for the amount of light. This is a third method where we're doing something slightly different. We're going to use gravitational lensing to find where the mass is after two galaxies collide and compare that to where we see the light and notice that it is different. So this is an image of the Bullet cluster where we had two big clusters of galaxies that slammed through each other. And we can measure where the stars are because the stars emit light. So we can use just where the stars and galaxies are. And what we see is when we slam two clusters together, for the most part, the galaxies are spread out enough that they don't hit each other. So the galaxies and stars just kind of pass on through and aren't really affected by the fact that these two clusters collided. The clusters also have a lot of gas in them. So there's just a lot of gas evenly distributed throughout each of the clusters. So when you slam the two clusters together, the gas from each cluster does run into each other and slows down. So the stars pass right through, no problem. The gas hits itself, hits the gas from the other cluster and slows down. So we can compare where the gas is to where the stars are. And then we can use gravitational lensing to figure out where the mass is. And what we see is that the gas in this Bullet cluster is represented by the pink here. So most of the gas it slowed down quite a bit. It hit each other and it slowed down. The stars wouldn't actually be included in this image, so they would have just kept moving through. So the stars would be kind of out here. This purple represents where all of the mass is, and it's between where the stars and where the gas is. So the mass in the Bullet cluster doesn't match the position of the gas or the position of the stars. So all of the mass in this Bullet cluster seems to be kind of between the gas and the stars. This is just showing this without trying to look at an image. This is one of the galaxy clusters as it passed through, the gas hit the gas in the other cluster and slowed down. The dark matter is pretty evenly distributed too. So the dark matter in this cluster hit the dark matter in this cluster and it slowed a bit, but not as much as the gas because dark matter doesn't really interact with anything, but it will slightly, just a little bit, interact with other dark matter particles, we think. So the dark matter from cluster A hit the dark matter from cluster B and did slow a bit, but not as much as the gas. And so the stars just pass through easily. So we observe where the gas is by looking in the X-ray. We observe where the stars are by looking in the optical, and we observe where the mass is by using gravitational lensing. And what we find is the mass does not match either the gas or the stars. So there must be, again, some dark matter, something besides gas and stars, that has most of the mass in these two clusters. So that's our third method. So we have rotation curves for spiral galaxies have too much mass for the amount of light. Gravitational lensing around elliptical galaxies show there's too much mass for the amount of light. And when we look at colliding clusters of galaxies, most of the mass does not match the position of the gas or the stars. One more method for detecting dark matter. But does anyone have any questions about bullet clusters and colliding clusters in general? Okay. So our last method, and this one is the most physics heavy, and I'm going to be honest, I don't 100% understand, but I want to mention it just to show you that there are a lot of ways we are detecting dark matter, and that's by looking at the cosmic microwave background. So at the end of our class on Thursday, I mentioned that there's this thing called the cosmic microwave background, which is what we see of the kind of remnants of the Big Bang, the really early history of the universe when everything was still very hot and dense. Eventually it cools enough that photons can escape it and travel through, and we can observe those photons now, and we observe them as this kind of uniform-ish microwave emission every direction in the sky, and that's what's shown here. So any way we look, we see microwaves that all have about the same energy that seem to be a remnant of this post-Big Bang, hot, dense universe. The energy of the photons we see corresponds to the density, the temperature and density of this early universe. So more energetic photons would mean a hotter, denser area of the early universe, whereas cooler or lower energy photons would tell us we're looking at a less dense, a slightly cooler part of the early universe. So we can see in these maps, they do have some variation. Some parts are warmer, they're represented by red. Some parts are cooler, represented by blue. And we can use the size variation of these blotches, these little blobs in the cosmic microwave background, to fit models of what the universe must be made of and try to determine how much dark matter there must be in the universe. So the big idea is that we can look at the size of the blob, we can plot kind of the number of blobs of a certain size is kind of what this y-axis is, versus the size of the blob, with these being smaller blobs, these being bigger blobs. And the shape of this curve tells us what the composition of the universe must be. So it kind of has to do with like the big blobs will eventually become galaxy superclusters, smaller blobs will eventually become galaxies. So in order to go from the size of these small blobs into galaxies, we need some dark matter to be there to hold things together, to pull in gas, to form galaxies fast enough so we see the universe as we do today, based on how things would have evolved from this early cosmic microwave background blobbiness. So that's my kind of hand-wavy explanation of that. But the main point is that the size of the variations in the cosmic microwave background are also a key observation that tell us dark matter must exist. So we have 4 different methods for seeing dark matter in our universe. All of them are different. All of them suggest that dark matter exists, which means that whatever dark matter is, it really does seem to be there. Before we start talking about what dark matter might be, does anyone have any questions about any of that? So now the kind of the big unanswered question is, what the heck is dark matter? And the answer is, who knows? But we do have some candidates for what dark matter might be. So that's what I'm going to try to hit on 3 of them, starting with machos and then also discussing WIMPs and axions. So these are where we get into the theory part of dark matter. We do not know what it is. We are pretty sure it exists because we have these 4 ways of seeing it, but we don't know what it actually is made of. So the first potential dark matter particle is the MACHO. MACHO stands for Massive Compact Halo Objects. So these would be things, this would be kind of our, maybe dark matter is just normal matter in these kind of planet-sized blobs in the halo of galaxies. So maybe out in the halo of galaxies, there's just a bunch of kind of planets without stars that we haven't observed because planets don't emit a lot of light, and they're just spread out enough that they aren't blocking the light from stars. The problem with this theory is that if there were machos, the number of machos we would need to create the amount of mass in dark matter, we should have seen them. So if machos were dark matter, we should have observed them, and we haven't. So machos were an initial theory, but we are pretty sure we can rule them out because we have stared at the halo of the Milky Way a lot and we have never seen one. And they would block light from stars, and we don't see these kind of periodic light disappearing of stars in globular clusters or galaxies. So there do not seem to be any machos in the halo of our galaxy or other galaxies, and we should have seen them if they were there. So maybe there's a few planets that get ejected from our galaxy, but there are definitely not enough to make up this huge mass difference between the amount of light we see and the amount of mass that must be in a galaxy. And I just had to, throw in Calvin and Hobbes because Calvin and Hobbes is great. And also astronomers are absolutely the worst at naming things. Machos is just one example of that. So the next particle that might be what dark matter is the WIMP. So we have machos and we have WIMPs. WIMPs are weakly interacting massive particles. And this is often put forward as the favored model for dark matter at the moment. But it doesn't really tell us a lot. It just means weakly interacting massive particle just means it's some particle that is about the same size as the W or Z boson from our standard model. So that's about it. It is not a W or Z boson, it just has the same mass. So that's interesting, but still doesn't tell us a ton about what dark matter is. The nice thing, the reason people like WIMPs is something called the WIMP miracle, which is when you say, I'm going to say my dark matter is made out of WIMPs, and you plug that into how we think the universe evolves, we get the right amount of dark matter if dark matter is WIMPs. So models of the universe, we can say our dark matter particle has this much mass and it's this likely to interact with other stuff. And when you put that into your big universe model, you get that if a WIMP is your dark matter particle, about 23% of our universe should be dark matter, which is what we see. So that makes it nice, but it doesn't tell us that dark matter is WIMPs. It's just kind of a nice detection that we see. We have potentially maybe detected something called the WIMP wind. So that's a good sign for this particle, but again, whether or not we detected it is a bit funky. So the idea of the WIMP wind is that as the Earth orbits the sun is also moving around the center of the galaxy. So the sun is moving through the dark matter halo in our galaxy, and while the Earth and the sun are moving in the same direction, the Earth should be passing through more dark matter than when the Earth and the sun are moving in opposite directions. So we're going around the sun as the sun goes around the galaxy. When both the Earth and sun are moving in the same direction, we should see more of a headwind of these dark matter particles. When the Earth and the sun are going in the opposite direction, we should see less of a headwind from these dark matter particles. So to do this, a few detectors, one specifically called DAMA, is set up in the mountains in Italy, and they have these very, very sensitive sodium ion crystal detectors to try to watch for just any change in the amount of particles that don't emit light passing through the Earth. The problem is there are other things that could potentially trigger detections. So neutrinos can sometimes trigger detections, and cosmic rays can sometimes also trigger detections. So what they're actually detecting is a little funky and hard to see. But their idea is if we see this kind of periodic variation over a span of 6 months, then that might mean that we are actually detecting the WIMP wind, because we would expect this every year. We should see more in June and less in December as we orbit the sun. And that is sort of what they have found. So this is the DAMA and updated Libra data, where they're plotting the number of detections versus time. So how often is their detector pinging and saying we moved through something versus time? And what we can see, especially in this update, when they changed from DAMA NA to DAMA Libra, there is this nice 6-month variation where their detections do seem to cycle over a 6-month period, which is what we would expect for this WIMP wind. The problem is there are other groups trying to do these same detections and they don't see this. So we have multiple detectors looking for the same kind of thing. One of them got a detection, the others don't. So maybe this is a mistake, but this is the maybe possibly one way we have detected dark matter particles on Earth. So worth pointing out, even though not conclusive evidence as of yet. So that's WIMPs and machos and how we might detect WIMPs through the WIMP wind. Any questions on either of those models? Okay. Not hearing anything, not seeing anything in the chat. Our last potential dark matter particle is the axion. So this is, again, kind of similar to a WIMP, but is much, much, much lighter. So axions would have a mass of 2 × 10⁻39 kilograms. So a proton is about 2 × 10⁻19 kilograms, I think. So this is 10 to the 20 times less massive than a proton. So very, very light particles. The fact that they're so light make them more difficult to detect than WIMPs. So one of the ideas with axions, people who like this theory say, the reason we haven't detected dark matter, if you don't believe DAMA, the reason we haven't detected dark matter is because it's axions. So we are looking for the wrong mass particle, and we just don't have equipment sensitive enough at this point to possibly detect axions. So the fact that we haven't detected dark matter particles yet is a positive for people who think that dark matter is made out of axions. The one way we might possibly be able to detect axions is that there should be conditions where axions spontaneously turn into photons. So we would somehow, if you have axions in the right electromagnetic field, then they should change into photons. And we can detect photons. Photons are light, so any camera detects photons. And that's what the people at the Axion Dark Matter experiment are trying to do. So this is an image of one of their detectors where they create a big electromagnetic field and have just a vat of liquid xenon, so something that doesn't interact with much. Xenon is a noble gas, so noble gases don't interact, are pretty inert, they won't do much. So anything they see, any photons coming out of this vat of liquid xenon could potentially be an axion decaying into a photon, maybe. So they're watching these vats with a bunch of very sensitive cameras called photomultiplier tubes and just watching to see if they see any photons. So far, they haven't detected axions. So they have this idea, we're trying to do it, but so far we haven't seen any yet. So if these are the dark matter particle, it's still possible. It might mean that our equipment isn't sensitive enough. It might mean that we haven't correctly figured out how axions could turn into photons. There's a lot of possibilities here where things could go wrong. But so far we haven't seen axions. So that's our 3 potential dark matter particles. We have machos, which we are pretty sure don't exist because we would have seen them if they did, those massive compact halo objects. We have WIMPs, or weakly interacting massive particles, which one group thinks they've detected through the WIMP wind, but also potentially other groups have done the same experiments and haven't detected, so that's not great. We want science to be replicable. And then we have axions, which we could maybe detect when they decay into photons, but so far we haven't seen that either. So we are still unsure what dark matter actually is. Any questions on any of that? So the last thing I want to mention before I set you free to finish up your dark matter questions is that there's one other way we might be able to detect dark matter, and that's at the Large Hadron Collider, or the LHC. And so this idea is, as long as dark matter is a supersymmetric particle, and what that means is that dark matter will be produced when we slam protons together, then we could possibly see it through the experiments at the LHC. So what the Large Hadron Collider is it's this big particle accelerator in Switzerland and parts of, I think, France. So it's this big loop that they're showing here on a map of Switzerland. And what they do there is they accelerate protons around this loop, get them moving really, 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 really fast, and then slam them into each other. When the 2 protons collide, they explode, and we get this, and as they explode, they turn briefly into energy. So if you slam them together fast enough, you have enough energy that after the protons explode, they can reform into new particles. We can briefly get new, heavier particles forming out of this energy. So energy and mass are equivalent. If you slam your protons together, they can explode and you can form new particles from the energy and the material that the protons were made out of. So in theory, if you slam your protons together fast enough, some of that energy and proton stuff could turn into dark matter particles, which we wouldn't be able to detect. But what we would see is that when we measure everything else that comes out of this explosion, we would have some missing energy and mass. So we slam our protons together, we measure a bunch of quarks and electrons that fly off from this explosion, but the amount of energy we put into that collision and the amount of energy that we measured coming out of it are not equal. There's something missing that could have been carried off in a dark matter particle. So this would just tell us about the mass of a dark matter particle. So far, we haven't seen this missing mass, but that could just mean that we aren't slamming our protons together fast enough. So for the WIMP model, WIMP people are saying we need higher energy colliders. We're not getting enough energy to produce the right amount of mass. The axion people would say we are producing dark matter, but the energies are so small because these particles have such small masses that we just can't detect this tiny amount of mass difference. So one way that we might solve that is by building the future circular collider, which is this big loop here. So this is not a particle accelerator that currently exists. It's one that's proposed in the future. So this would be one that is much bigger than the LHC. Having a bigger one means we can accelerate the particles to faster speeds, greater energies, and potentially actually produce dark matter. So maybe we can detect dark matter through things like DAMA, which are looking for the WIMP wind. Maybe we can detect dark matter through things like the Axion dark matter experiment, which is looking for these axions spontaneously turning into photons. And maybe we can detect dark matter by looking for missing energy at the Large Hadron Collider, whichever particle you want it to be. And yeah, that's the Geneva is right here. So this is a huge thing. I don't know the actual radius of the future circular collider, but it would be very, very big and cost billions of dollars to make. But would be pretty cool. Could potentially answer more questions about what our universe is made of. Any other questions about anything? Okay, so now you should have enough information to finish up this activity. So question 5, you're just gonna pick your favorite of those 3 dark matter particles, so machos, WIMPs, or axions, and tell me why. And then questions 6 through 7 walk you through a bit of math to figure out how much dark matter there currently is in the Earth. So we think dark matter is pretty evenly distributed throughout our galaxy. So the idea is we can figure out the density of dark matter and then figure out how much would be in the volume of Earth to see exactly what that number should be. So I'm gonna reopen breakout rooms. So you can go in and finish this up, and then we will briefly come back together around 12:45 or so to just debrief together and finish up. Okay. So rooms should be open. Volume, and then density, you get mass per volume. It should be a pretty small number, and even when we convert it to kilograms per meter cubed, we should be getting pretty small numbers. But the idea is if you take this small density number and multiply it by the entire volume of our galaxy, it's pretty big. So even though there's only about 12.8, 12.9 kilograms of dark matter passing through Earth right now, so about 26 pounds of dark matter passing through Earth, there isn't Earths all the way through our galaxy. So there's quite a bit of empty space in our galaxy that does seem to have the same amount of 26 pounds of dark matter. So just a kind of fun little thing to consider how much dark matter is in Earth right now. You could use your own volume and figure out how much is passing through you as well, if you wanted to. Besides that, please do remember as you sign off to submit a really short statement, either with I know what my project is and it is this, or I don't have an idea yet, but I really liked talking about stars, or I think fusion is really cool, or I'm a rhetoric major, how can I work with that? Or I really like photography, can we relate photography to science, to astronomy, like whatever you want to think about, I should be able to relate it back, probably. So please do submit that just so I can see where you are, how you're feeling. And otherwise, keep working on your labs and homework. We have covered all the material in all of the labs. So all of those should be fine. And we've done most of everything in the homework. There's one question about NASA missions that we haven't covered yet, but you should be able to address everything else. And if you have questions, always email me. I will get you a study guide soon. Sorry, running through my list of things I need to say. And otherwise, have a fantastic weekend, and I will see you on Tuesday to talk about NASA missions.
Thank you.
Bye, thank you.
Thank you. Thank you.